Hey everybody, thanks for joining today. I really appreciate you guys joining. A couple of years ago, I actually was there in person, so I'm very much looking forward to being there again, as soon as possible. I had really fun memories and I met a lot of really smart people at the conference a couple of years ago, so that was really fun. My name is Luis. I work I'm the CTO and co-founder of GRID.AI. And today I'm going to be talking about our open source projects, two of our open source projects called Lightning and Flash, and also a little bit about what the problems we're trying to solve on Grid, how Grid's architected, kind of how we're thinking about the problems faced, and our current solutions there, and how kind of those two things come together. And, of course, for this community especially, we want to open it up for your feedback and anything you can offer on that end. So my name is Luis, and here's my very nice daughter. And the first project that I wanted to demo you guys is something called Lightning. You might have heard of Lightning. I'm sure some of you have used Lightning before. And the idea of Lightning is to work as a simple wrapper around PyTorch. So PyTorch, it's one of the two major AI frameworks today, together with TensorFlow. Yet PyTorch is the one who's been kind of increasingly becoming more popular with the research community, and Lightning provides kind of this lightweight wrapper around the PyTorch experience, making it a lot more efficient and easy to work with. And the same idea, the simple idea of PyTorch of Lightning is that models. Is that everything's modularized, but primarily the idea is that when you define models, they work in a simple class, and then you separate the main areas of work into their appropriate abstractions. So it's easy to share with others, it's easy to develop the code, and also it's easy to utilize a lot of other advanced techniques that the community has provided in different areas. So let me just kind of summarize and jump right into them so you can really understand what's going on. But the basic idea here is that we provide three major abstractions. There's a lot more, but the main idea here is that you can divide your deep learning or AI code into sort of these three major abstractions. Two, which are sort of inherited classes. So when you define a class, you inherit these two classes that we created, and then they sort of provide superpower for those classes, and they abstract a lot of the boilerplate away from the steps that you want to do. And these are the model that you want to define and the data. So here's called a Lightning module and the data module. And then we provide this workhorse, which is the trainer, which is kind of this very simple abstraction, which is very feature-rich with all sorts of integrations with loggers or advanced model sharding and so on, that help you train the model. So you combine both the data and the model, and you train them. And let me just jump right in, because I think this is kind of really what I like the most about working with Lightning, is that even if Lightning is designed to help, it was originally created by Will, my co-founder, William Falcon, while doing his PhD research at NYU. And the original intention was to help AI research not focus too much about certain engineering boilerplate tasks, such as dividing data between GPUs, connecting GPU processes, etc. So it still kind of has that flair of being dedicated to the research community. Yet, as you can see, I'm sure that if you used PyTorch before, this will be kind of a fresh, it will look very, very welcoming. So the basic idea is that you have to define these three things. So you define the model using the Lightning data module. You define your data. This is optional, but I really encourage you to do so, because it makes things a little more encapsulated and easy to work with. And then you combine those two things and use the trainer to train your model. And it's as simple as let's import Lightning. And here I'm going to be creating a very simple classifier. Or actually, I'll be creating a very simple classifier with MNIST, a very small data set. And here's how it works. You inherit from our data module class, and this class comes with a number of hooks and methods to work with different stages of the pipeline. And here I'm only defining 3 of the stages because these are the ones that I want to use in this example, but you can define many more. For instance, I define in my init function, I define the transforms that I want to apply to this data. So if you're used to PyTorch, these are common transforms that you can do. Then there are 2 pre-processing steps that I want to apply. One, if the data doesn't exist, just download it. And second, just split it into my training set, my validation set. And I could do that in this step that we call setup. So basically, it's kind of all the pre-processing is nicely encapsulated inside this methods. And then you can provide a number of methods that are used to create data loaders for the different stages of your training process. In this case, I'm just creating a train data loader, which uses the same semantics of PyTorch. But different than using this kind of as random methods, it's not just very nicely encapsulated. And then the second step is to define the model. And the model, if you ever work with PyTorch, is very similar to working with PyTorch. The main idea is to create a forward method that runs through your network. And then Lightning provides a lot of other common hooks or methods that are automatically used depending on how you call your training process. So in this case, I'm just saying a training step. So this is what I want to happen whenever I train, on each step of the training process. And here is a method that I define the optimizer, whatever I am optimizing against. And this is kind of a very minimal definition of this, but there are many other things that I can define. I can define what happens in the validation step, or whenever the app ends, or whenever it starts, whenever training ends. So there's just a lot of these hooks that are available so that you can sort of configure different stages in the training process. And the more advanced user you are, the more you're going to benefit from this. And if you are a PyTorch user today, what you're going to notice is that there's no need to define device or where this is going to go. There's no need to define complex training loops or call backward manually. All of this is taken care of automatically for you. And the power of it is it also integrates as you scale. So you can start with no GPUs, and then you can train 1 GPU in 4, in 100 GPUs, in a TPU. So and with no effective code changes, so the definition remains the same, which is really nice. So let's define these 2 things. So I define my data and I define my model, and now we can put it all together. I'm just going to import them. I define these 2 little scripts, and let's instantiate them. And now here, when I create sort of instantiating my workhorse, I tell the trainer what I want it to do, right? So in this case, I say just train for 1 epoch, but the trainer is really kind of how I can configure the training process. So I can pass in loggers or a number of different techniques such as early stopping or different plugins, which we can talk a little more later. But this is sort of the workhorse. This is really what trains your network. And in this case, it's going to tell me, hey, you have GPUs available, but you're not currently using them, and you don't have TPUs available in this kernel. It's okay. And it uses the same sort of keyword. It's been used for a long time in scikit-learn and other frameworks. And you just pass the model and you pass your data, and that's it. It will just train your model as is. You respect the parameter. In this case, you say max epochs. And as you notice, I don't have to call things manually because I've defined things like validation step and the validation data loader. It will automatically run through those processes in this epoch. And of course, it generates automatically TensorBoard logs. Let's see. Let's see where are my logs, which I can then use to see on TensorBoard. I think I'm in the right instance. Well, I can use TensorBoard logs, or you can then combine with, or you can use the other loggers of your preference. So I really like to use 1DB or sometimes CommonML, and you can just very simply add them in the trainer. Now I think a lot of people, a lot of our community, the Lightning users, what we've noticed is that folks what they really appreciate is this idea of, okay, I've defined my model and I define my data, and now I've trained in, let's say, a resource constraint setting, such as a CPU machine or my own laptop. But now I want to grow and I want to train in a much more powerful machine. So in this machine that I'm running, I have 4 GPUs available, 4 T4 GPUs, and I want to use the power of these 4 GPUs. And I think this is really what makes it important, because lining, you don't have to define, the device or the training loop or any of those things. You just pass the keyword GPUs 4 in this case, and I'm telling the trainer, use all of the 4 GPUs in this node. I can tell many other things. I can say, hey, use the CPUs or use GPU 0 or different kinds of GPUs. But in this case, I'm just telling you, just all the 4 they're available. And just with the simple modification, the simple parameters, now I can use all of the GPUs that are available and train all of them. I mean, this is a very small model and very small data set. So, the benefits are not really that noticeable. But if you were to train, let's say, a very large model, you will really notice the difference of being able to use the 4 GPUs at once versus just using, let's say, a CPU. Now, lining, it's really, what I'm showing here is kind of just the very basics of what you can do with lining. But it comes, the magic of it is that, especially at the workhorse level, it comes with a number of plugins and integrations that make your work really easy. So the goal here is for you to focus on model definition and training and the data pipeline, and everything else such as logging, it's taken care for you, either because the community have added the solutions, or because of of the lining team have collaborated with a bunch of people to add the solutions. For instance, you can add a bunch of loggers. So in this case, you can add MLflow, ComML, or weights and biases. And it's as simple as just pass the keyword logger, and you can add all of them. So you can log for TensorBoard, Comet, weights and biases, MLflow, everybody at once. And there's no further modification. You don't have to specify any other magic keyword. You just say here, you say, hey, in this particular case, I want to log this dictionary. So it will parse this dictionary and send you all the loggers in the correct format. So it's kind of, there's no additional work for you in order to add this loggers. Or you can use more complex techniques, such as I want to use 16-bit precision. And this will automatically use the now native PyTorch 16-bit precision training to train your model, which is very useful. Your model can train much faster. Or you can profile your model. Or if you have TPUs available, either on Colab or GCP, you can use TPUs. The same idea with GPUs. You just say how many you have available and how many you want to use. Or this is kind of more recent additions and much more advanced additions, which are very useful for training very, very large models with trillions of parameters. You can pass these plugins. In this case, I want to use a deep speed, which helps me shard the model in the different GPUs that I have, and I can combine that with precision and the different GPUs that I want to use. So lining comes with a ton more features. This was kind of a very quick demo of the things that we can do. But if you are not familiar with lining, and if you're engaged in sort of developing more complex models, you're definitely going to, in PyTorch, you're definitely going to benefit greatly from using lining. And the community is extremely active. There are features for both novice PyTorch users and also very, very advanced PyTorch users. So I both encourage you to use it and give us feedback. We'll love to have you be part of the community. Let me open this a bit for a few questions. Let's see, Andrew. Equivalent. So Andrew is asking, are you able to specify the strategy for multi-GPU training? That's a good idea. So the answer is lining. So by default, you can specify different strategies for training using the trainer. However, you will use the common techniques that are available at PyTorch by default. So you can use something called DDP, which is a data parallel will shard the data and then make that data available on the different GPUs and the different nodes, and then a number of other techniques that we're continuously implementing. Now, the good thing is that you can implement your own techniques if that is something that is very important to you. So it's very easy to implement new kind of distributed techniques using the Lightning API, and we encourage folks to have kind of that advanced use case to do so. I'm hoping that that answers your question, Andrew. So Lightning is especially, I mean, if you're unfamiliar with PyTorch and it's kind of your first experience with PyTorch, it will be a very good experience with PyTorch. The API is a little different than TensorFlow, and some of the abstractions are a little different, but Lightning provides kind of is just the perfect companion for advanced research of PyTorch. And the community has created a number of very an array of both complex and simple examples that could definitely address your use case. And the main idea, the main philosophy of Lightning is this of providing you the maximum flexibility, so you can do things as complex as you wish. So you can create different optimizers, or you can create combine different networks in one, or a number of different very advanced techniques, yet avoiding all the common boilerplate, such as writing manual training loops, or let's say assigning things to the right device if the thing is there, or calling backward manually. So all of those things are completely taken away from you, so you can focus really on the core of your model. And it comes with just a ton of features, and the community is adding so many features every day that it's just really, really nice. For advanced use cases, it comes with just a number of tricks that will just make you much more effective training. And also, it includes a lot of recent additions for production use cases, such as Onyx Export or TorchScript, which is a sort of a compiled version. It runs it in a C++ engine in case you want to deploy your model elsewhere. So all of these things are really automated with Lightning. Lightning is kind of a really nice way to work with PyTorch today. Now, the really nice thing of Lightning, really, or the biggest advantage of Lightning today is its community. I mean, it's a very fast-growing project, and because of the way Lightning is done, it's very easy to build on top of it. So we have a number of really amazing projects that are built on top of Lightning. More than 3,000 GitHub repositories currently are built on top of Lightning, and a number of these are really, really great libraries, such as NVIDIA's NeMo's framework for conversational AI, or Lightly, which works with self-supervised vision problems, and PyTorch forecasting, one of my personal favorite projects, very early days, but personal favorite projects that deals with time series forecasting problems. So Lightning is one of the fastest growing projects also in this space, and it's just been really wonderful to see how the community has adopted the project, how much is being used every day, and the great kind of contributions and feedback that everybody shows. From more than 500 contributors around the world. So if you're interested in developing Lightning or helping with these problems, you're going to find a community of really supportive and really helpful individuals. So while Lightning was designed for this kind of advanced use cases, or was inspired for advanced use cases from the beginning, we took the learnings from Lightning and we created a new open source project called Flash, which is really designed for the applied AI use case. And Flash is really kind of, it targets folks who really are not engaged in research as much, but would love to apply the latest techniques in a very organized way, in a very sort of intuitive way in their current problems that they have. So if you take the abstractions that are created by Lightning, Flash creates one abstraction sort of to rule them all, and this abstraction is called a task. And the idea of a task is that you can define all the pieces of your problem inside this one class, and this will encapsulate the complexity of solving that problem. And let me show you what I mean by that. So different than Lightning, that kind of, you can use, it's fully compatible with Lightning, so you can import anything with Lightning into Flash and vice versa. But the idea of Flash is that when you create these tasks, that they fulfill sort of this function, right? So they solve this particular problem. So we provide a number of out-of-the-box classes. For instance, a translation task, a summarization task, a tabular classifier, a video classifier, and so on. And what they do is they integrate with other great libraries such as Hugging Face or PyTorch Video to solve a particular problem. And here's how that works. In this particular case, let's say you create a simple classifier, and you can see that's similar to Lightning, but much simpler. And the task definition just takes all those pieces that make that task, in this case, my model, and my loss function, and my optimizer. And this is kind of how I define my task, kind of very simply. And then using sort of the same trainer of Lightning, I can then train, let's say if I wanted to train this model, I could just train that model with this task. But what's cool about it is that it comes with a number of predefined tasks. So for instance, if you wanted to use one of a cutting edge summarization model, you can just load the summarization task. And then you can fine tune it, for instance, in your own data. And this is sort of a wrapper for Hugging Faces, tokenizers, and models. And it makes it really easy for you to define that model and fine-tune it with your data. So there's just a word called fine-tune. You load your data from CSV files, so it's very straightforward. And by combining both of them, you can sort of have a edge state-of-the-art model with a very, very simple abstraction. So basically the idea here is that if you are really engaged in research, we encourage you to use Lightning. But if you're today just trying to solve, let's say, a summarization problem in a business context, Flash is just the perfect tool to get started because you just have to define very few pieces, right? So you just have to put that in a certain format, load one of the predefined tasks, and off you go. So it's very straightforward. And Flask also takes special care of the prediction pipeline. So let's say that I want to translate, I want to run a translation task. Either you can fine tune it, or you can load a checkpoint from our community generated checkpoints. But because the task already knows what to do, it's already defined with the logic to load the model in. It's very simple to just load that from, let's say, an S3 location or from an URL, and then just call predict on, let's say, a list of sentences. And this particular model was trained to predict between English and Romanian. So it's very simple to pass, let's say, a list of sentences to do that. So let's see if we can do that, actually, because I really like the predictions that the model generates. Working. All right, let's take a look. So, the goal of Flash is really to simplify the the baselining or the experimentation with cutting edge techniques. And it creates, by creating this abstraction of tasks, either you can create new tasks on your own, or you can contribute back, or you can just find out of the box tasks. And the goal of the Flash community is to increase both the number of tasks or the things you can do with Flash, but also the number of techniques that are available in each one of these classes. So for instance, let's say in the translation task or in the image classification task, you could use different backbones, including cutting edge models, such as vision transformers or GPT. And then also in the same sort of encapsulated task, you can compare something that is very cutting edge with a more traditional classifier. So it's kind of this very simple abstraction for the problems you want to do, and without having to deal with many of the complex data pipelining or model definition steps that you would most likely have to do otherwise. So Flash is a very new project. We just launched a few months ago, so please download it, give us a lot of feedback. We have a taskathon coming. So if you're interested in contributing new tasks, please reach out, because there are many tasks in different domains that we'd like to add, such as time series forecasting, or different problems in the space domain, or 3D geometry domains that we'll love to add to Lightning, to Flash. And there's just a lot of people really interested in kind of this very simple interface. So yeah, if you're interested, please reach out. And I think the way I think about these two libraries is, task is the place where you want to start trying something new. If there's a new model or a new implementation, and you don't have enough time, or sometimes dealing with a lot of research code can be very complex, Flash makes it really easy for you to get started. So let's say if you wanted to run a video classifier, you don't have to download a really complex PyTorch model for that. You can use the Flash task, the video classifier task, and that's a really good starting point. And then from that point on, you can fine tune it. You can try different backbones, and you can move to more complex use cases if you wish. But for a lot of use cases, we see that this is just enough and what people need. Yeah, Andrew. So if it has prepackaged architectures for Flash, yes, actually, yes. So it contains quite a few. In the different domains, it contains prepackaged architectures. Yes, and let me see if I can give you kind of a glimpse of how that works. Yeah. So for instance, the video classification, it contains a number of backbones. Let me show you. Let me see. Let's see. Actually, let me open the docs. So in, let's say, image classification, it provides a number of different backbones today. So from different combinations of ResNet to even more modern implementations from TIM, which is it's a very popular image classification library, and even more modern designs like vision transformers. So it comes with a bunch of them already integrated, and you can pass different backbones. You can define which backbones you want to use. I'm looking for an example in their documentation. There you go. So here's kind of the idea. So let's say with an image classifier, you can define different backbones to use, right? And in this case, we provide a number of them. Usually kind of we stick to the ResNet implementations and a handful of others implemented with integrations with TIM. But it's very easy for you to also add your own backbone. So you can register using, Flash makes it really easy for you to register a new backbone. So you can combine it with the ones available in Flash and then see whatever works best for you. So in this case, for instance, I can register a new backbone, and I am just using a backbone that is already available in Torch Vision, so implemented elsewhere. And I can use the same abstractions of Flash to compare with this other backbone. So there's, in certain tasks like video classification, we don't have yet that many backbones, or in other areas there aren't that many backbones, but I mean, that's an area of really active work. So if you know, if you're interested in that area, we'll love to collaborate, because we'll love to implement as many backbones as possible. So it's really easy for the community to get started. But yeah, the idea is that is that simple. You can basically either use the backbones available or register new backbones that other people have created elsewhere, and use kind of the same interface, the same task interface, to both train and run inferences. Oh yes, thank you. Yeah, Andrew, so the question, how many, I don't know off the top of my head, because there are different kind of tasks in different domains, from translation to classification to video classification and so on. So yeah, I would say there's quite a few, but I don't know off the top of my head. But yeah, it's an area of very active development, so we'll love to work with you if you're interested in adding more different kinds of architectures or backbones to our tasks. Cool. So the last thing I wanted to demo is, so both Lightning and Flash are part of our open source projects. We have a number of other open source projects, such as Storage Metrics, and many more coming down the line. And we really believe as a company that kind of the power is in open source, the power is in the community. So we want to contribute as many open source to what we think is sort of last mile problems, like when you're either creating the model or developing the model locally. So all of the solutions will always be open source when they come from GRID. And then we're helping those that want to scale their workloads from, let's say, working on their laptop or working on, let's say, Colab, to really massive scale. So either they want to train things in lots of GPUs, or they have very large data sets, or there are many people working on the same problem. And that's why we created GRID. And GRID has three problem areas that we're tackling. So first is the problem of data. GRID helps you organize data and create data sets that you can then use for both creating a model, sort of in the research phase, or training very large models. So today we provide something called a data store, which is a version storage for data sets. It supports multiple terabytes, and it's designed for high performance data rate support. So I'll tell you how that works and how that's engineered in a moment. And then the second problem that we're really trying to solve is the idea of compute. In the deep learning and AI space, you typically need not only a lot of hardware resources, like GPUs, but also sometimes you just need to be able to scale them very quickly, to add hundreds of nodes so you can explore, let's say, different hyperparameters of a model, or you just one single model can need many GPUs to train. So the idea is on compute is, how can we create a service that orchestrates everything for you, so you don't have to worry about dependency management or container creation or logs or artifact, any of that, right? So if you're using any solutions, Lightning or otherwise, how can we make that as easy as possible? And the last one, which is the key piece in the space, which is the idea of collaboration. Today is sometimes very difficult to collaborate in the AI domain, because it combines both the software development piece, which let's say you can use something like GitHub to collaborate on, but then you have a lot of the interactive and the training process, which becomes really sort of difficult to track. So things, what experiments did I do, who did it, what were their metrics, what were their artifacts, and so on. So we bring these three pieces together, and we're creating now a service that helps you collaborate, creating new AI models. And sort of this is how we think about it in terms of architecture. As a user, you can use any solution. You can use, whatever you want. You can use TensorFlow or Keras or scikit-learn and so on, or Lightning. And the idea is that you come to a service, GRID.AI, and then you link your own cloud account. So that can be AWS, GCP, Azure, and soon we're adding support to local clusters. And using this one interface, you can schedule workloads in any cloud provider, in any compute hardware that you may have, and Grid will orchestrate everything around it. So maximizing both the cost and efficiency of whatever you want. And the way in which we do that in cloud providers is that whenever you link Grid, the service, to your cloud provider, Grid will then create a number of Kubernetes clusters, depending on your needs, typically one, but sometimes many, that will host the main things that you're going to use to develop your experiments and your model. So these are sessions, which are kind of JupyterLab powered nodes or interactive sessions that we call, or you will run hundreds of experiments in TensorBoard, but all inside, highly customized and optimized Kubernetes clusters. And then we also manage everything from artifact tracking and logs. We put everything on S3. And also we organize your data stores on S3, but also create a number of high performance volumes that we can then attach to whatever you're working, either your session or your experiments. So all of this is done by Grid in a hosted service. So the idea is that you can just link your cloud or connect your whichever account you have access to, and Grid will do all of its orchestration, but without your data ever leaving your cloud account. So everything is sort of encapsulated there, and using a hosted service, Grid can control, can orchestrate whatever is inside, but the actual data never leaves, just metadata. Say what time you start something, what time, how long did it run for, and those kinds of things. But let's say if you were to remove this connection, Grid loses access to everything, so Grid would not be able to see anything that's inside. So it's the best of both worlds, because from an MLOps perspective, you don't have to manage Grid as software. So there's no sort of management requirement on keeping it up or connecting to a database. All of this exists as a service outside, and what's inside your infrastructure is all of your data and all of your compute, and all the clusters are actually running inside your infrastructure, which you can have access to, of course, because it's your own account, but the orchestration layer stays outside, which makes it really cost efficient. And we think this allows teams to grow significantly and be able to collaborate effectively. So I want to show just a little of how that works today. So you can use this today. So there's a community edition of Grid. So by all means, please come and use it and give us feedback. And but what I'm going to be showing is how it works when you link your cloud account, which is a feature available for whenever we have a partnership. And the idea is that whenever you link your cloud account, Grid goes through this phase of setting up your cloud account. So creating the clusters and so on, and setting up the right permissions. And then from that point on, you can orchestrate, you can create data stores, which are this highly optimized data sets that you can then mount in your sessions or experiments. Or you can start sessions or experiments. Sessions, what we call sessions is the idea of creating a node. So we provide full support for all of the GPU instances and cloud providers. And you basically have access to the entire node. So like what you would do, let's say if you were to start an EC2 instance, but with a lot of niceties, like very recent JupyterLab instance, cost tracking, you can pause them and preserve the file system. It's integrated with your Git account, GitHub. It automatically provisions SSH. So kind of a lot of really nice things that you can do. And with a lot of amazing upcoming features, such as being able to upgrade the instance as you're working with it. So let's say you can start in a CPU instance, and then you can move to GPU and so on. I think what you can do with instances is it will help a lot of people, because today we see that even in your cloud account, going through the work of setting it up is very complicated. But the magic of Grid really is on being able to run experiments without any code changes. So imagine that, still using Lightning, I am developing a model on GitHub. In this case, it's a model to predict cryptocurrency prices. And it's a simple model that I just run locally. I don't want to integrate with anybody. I am just training this model locally, and it can be any model, Keras, TensorFlow, anything. And then I create an entry point script. In this case, I called it train, and it has just a few flags, such as learning rate and hidden size. So GRID was designed for you to be able to run experiments without code modifications just by calling the scripts. And the easiest way is we provide these badges. Let's say when you run something and that effectively runs, that builds correctly, and it runs successfully without failing, then you can take these badges, and they're sort of a very easy way to reproduce your work elsewhere. So in this case, when I click on a badge, I can start a new experiment from that exact Git, exact infrastructure, the exact same script, and you can see the same invocation parameters that I use, and so on, and in the same cloud provider. But I can use a different cloud provider. Let's say if I don't have access to your cloud provider, I'm not your team member, and I wanted to run the exact model that you ran, but in my infrastructure, I can just click on that button. But GRID also provides this rich CLI, so that you don't have to sort of click on a button on GitHub. You can, say, work directly on a GitHub repository, and let's say you SSH into the machine that you wanted to, or you're just working locally, and then you can call, we have this command called grid run with our CLI, that you can just run your script as is and just pass its native parameters, and it will run on this remote infrastructure. And you can configure, let's say, you can tell GRID, use pod instances, because I'm okay if they're taken away, but I want to really save money there. And I can specify, say, I want to run on this particular cloud account, let's say on AWS for my university or for my work, and I want to use this particular instance type. I want to give this many GPUs to this job, and that easy. We'll just go and create it. You don't have to create any Docker images. I mean, we're providing more support for detailed definition of Docker images, but a lot of folks have given us feedback that the less they have to manage Docker images, the better. So what we try to do is we try to make sure that the requirements are set, but we don't force the building of Docker images. We do our best to introspect the repository to identify the dependencies that are needed, and then we automatically build the right images for you. And then we automatically, of course, scale the cluster and wait for everything to be running effectively. So now running one experiment is kind of the basics, right? So you want to run one script, but GRID supports this idea of running hyperparameter sweeps with also no modification to your code. You don't have to write a specific script. You can just call that sweep directly with the CLI. And I want to show you what happens after you run that. So in this case, GRID keeps all the metadata, the things that are running my own cloud account. And this is how we help you collaborate with your colleagues, because your colleagues can go and see the things you ran and download the artifacts and so on. In this particular case, I ran experiments. I ran a sweep with 15 experiments in different hyperparameter combinations. And I want to see I want to see everything that happened there. So I want to see the hyperparameters that were used. I want to consume the logs of that specific experiment. So whatever was printed to discern output or an error. And I can do all of that either through the CLI or the web UI. And we're just coming out with an SDK that helps you do that in kind of a more refined way, in case you want to, let's say, do in a different environment. And without having to start any machines, we did all of this automatically. And also, what I really, one of the things that we really like is that without having to modify code, we think that we can do so much For instance, in this example, I trained this model, which are trying to predict cryptocurrency prices. And I generated TensorBoard logs in the file system, and we will automatically look at those logs, interpret them, and then parse them and display them in the web UI and make them available in an API. So you could use those logs for something else that you wanted to, like creating complex training systems, or just tracking what happened, let's say in the past, if you wanted to go a few weeks back and see how something performed, as well as the file system. So without having to modify anything, we observe the file system and we track all the artifacts so that they're correctly stored, even if you ran something months ago. So it makes it easy for you to work with whatever you ran in the past. So in this case, this particular experiment generated all these artifacts, and we just observed the file system, and we sync kind of two ways, much like Dropbox does. So if you delete something, it's also deleted from your bucket, and you just don't have to worry about that. And we also provide sort of this cool integration in TensorBoard that you can combine both running experiments and stopped experiments into the same TensorBoard session, and you can kill it anytime. Because we observed that, and it today is quite difficult to do that specific operation. Sometimes you want to do that. And finally, given that kind of the CLI works everywhere, you can then go back to an interactive session, to a Jupyter notebook, and explore your trained model or explore its checkpoints as it is training. So in this case, I download the checkpoint, I start my model, and I just want to plot a few predictions just to see how it's doing. And it turns out it's doing okay in a few cases. But it's kind of, we were really thinking hard about kind of this problem of how can we combine the workflows of something interactive and something that you run a lot of sweeps on. So yeah, GRID's all about the community. So we'll love your feedback. So if you want to come and use it, you're more than welcome. We'll love to hear your feedback and anything you have to say, even kind of how we're thinking about these problems. And for the folks here, we'll love to give you guys some credit just to help us there. And also to join us on Slack. I'm sure your ideas are really valuable for how we're doing things and how we're thinking about problems. So we'd love to have you join and talk to us about those challenges and sort of the future of the industry. Yeah, so I'd love to kind of answer any questions if you have any. I think we're right out of time. So if you have any questions, I'd love to answer them. I think the right way to interact is to use sort of the sessions panel here on the event. So yeah, if you have any questions, just post them there. Otherwise, have a good day and the rest of conferences. I will actually join a couple of other demos that are coming shortly. It's really nice to come here and present. I am looking forward to being in Toronto maybe next year, whenever things are a little calmer. Thank you, David, and for the invitation. This was fun. I think this is kind of a very good, successful online event. I'm very much looking forward to being in person again. And I would love to, hear back from you. So please reach out. So my email is luis@GRID.AI, or come and visit us at GRID, and we'll love to get to know more and discuss these problems in a bit more detail. Awesome. Thanks, everybody. Thanks, Shashank. Yes, any thank you guys need. Okay, so I'll pass back the word to Faraz. I think this is a good time for us to hop out. I don't think I have control of the recording, but I'll love if you could, share it with me and others. It was a really cool, kind of very nicely organized presentation.
Thank you, Luis, for the great demo. That was really good. questions, we can just jump off. And like you mentioned, the recordings will be shared with the team and the attendees as well.
Awesome. Yeah, looking forward to all the demos and the rest of the conference.
Thank you so much. Bye.
See ya.
Bye.